James Webb Space Telescope spotted a large object about 10 light years away moving toward Earth. The posts claim that the telescope captured the object changing its trajectory.
The James Webb Space Telescope has once again shaken the world of astronomy, confirming an event so rare and staggering that it feels torn from the pages of science fiction. The interstellar object 3I Atlas, first detected streaking through the solar system on an unusual and erratic path, has now been verified by Webb's instruments to be on a collision course with Mars. The confirmation has sent a ripple through the scientific community, sparking feverish activity among astronomers, planetary scientists, and astrophysicists who are racing to understand both the nature of this mysterious object and the unprecedented implications of its impending encounter with the red planet. Before we start, hit the like and subscribe buttons for more updates.
Astronomers are continuing to track a newly spotted object, likely a comet, from outside our solar system. The interloper, named 3I Atlas, was first spotted on July 1st.
The journey of 3I Atlas has fascinated scientists since its discovery. It is the third known interstellar object to visit our solar system, following the enigmatic Oumuamua in 2017 and the comet 2Y/Borisov in 2019. Each of these objects arrived from beyond the solar boundary, carrying clues about the chemistry and physics of other star systems. Yet, while Oumuamua puzzled scientists with its strange tumbling motion and comet-like acceleration without a tail, and Borisov resembled a more conventional comet despite its interstellar origin, 3I Atlas has proven to be far more unusual. From its erratic trajectory to its unpredictable acceleration, it has defied many of the established models for interstellar travelers. Its behavior suggested powerful outgassing or magnetic interaction unlike any comet or asteroid ever observed. What no one expected was that this cosmic vagabond would not merely pass through, but intersect directly with one of our neighboring worlds. When the Webb telescope turned its gaze toward 3I Atlas, its instruments captured data at a level of precision unmatched by any previous observation. The near-infrared spectrograph, NIR-SPEC, and mid-infrared instrument, MIRI, recorded the object's composition, surface temperature, and trajectory in minute detail. Over successive weeks, astronomers refined their calculations, adjusting for gravitational perturbations from Jupiter and solar radiation pressure. By the time the orbital projections stabilized, the verdict was clear. The path of 3I Atlas would intersect Mars's orbit almost exactly. Even accounting for uncertainties, the probability of impact exceeded 99%. Webb had confirmed what ground-based observatories had only begun to suspect. A direct collision between an interstellar object and another planet was imminent. The implications of this confirmation are staggering. Never before in recorded history has humanity had the chance to witness an interstellar object physically striking a planet within our solar system. The event promises to be a cosmic laboratory unlike any other, offering a rare opportunity to study what happens when material forged in a completely different stellar environment collides with a terrestrial world. Mars, already a planet of immense scientific interest due to its geological history and potential for past microbial life, will now serve as a natural testbed for high-energy astrophysics, impact dynamics, and planetary evolution. The excitement among scientists is tempered by the gravity of the event. 3I Atlas is estimated to be between 2 and 5 kilometers in diameter, large enough to cause global-scale effects on Mars, though not large enough to destroy the planet. Its mass and speed, however, make it one of the most energetic impactors ever recorded. Traveling at tens of kilometers per second, it will release energy equivalent to millions of megatons of TNT upon impact. The shockwave is expected to carve out a crater hundreds of kilometers wide, vaporize vast amounts of Martian surface material, and eject debris into orbit and beyond. Instruments already in place around Mars, including orbiters from NASA, ESA, and China, are being recalibrated to capture the event in every possible wavelength of light, from X-rays to radio waves. For the first time, humanity will be able to observe the instant of interstellar collision across multiple instruments simultaneously. The Webb Telescope, positioned at the L2 point, will continue monitoring in infrared, while the Mars Reconnaissance Orbiter, MAVEN, and ExoMars will provide real-time telemetry from orbit. Even the Perseverance and Curiosity rovers, though distant from the predicted impact zone, are expected to record atmospheric changes and seismic vibrations transmitted through the planet's crust. Mars, which has long stood as a silent witness to billions of years of cosmic bombardment, will now host a collision that could rewrite planetary science. One of the most profound scientific implications of this event lies in what it may reveal about interstellar chemistry. 3I Atlas, having spent perhaps millions of years drifting between star systems, carries within it pristine material untouched since its ejection from its home system. The spectroscopy conducted by Webb has already revealed exotic signatures, traces of hydrocarbons, carbonates, and even volatile compounds that do not match typical solar system isotopic ratios. When the object strikes Mars, the collision will vaporize much of its mass, but fragments may survive, embedding themselves within Martian regolith. These remnants, accessible to future Mars missions, could provide the first tangible samples of material from another star system ever found on a planetary surface. The impending impact has also reignited interest in planetary defense and celestial mechanics. Although the collision poses no threat to Earth, its occurrence raises urgent questions about how well we can predict or deflect interstellar intruders. Objects like 3I Atlas are notoriously difficult to detect early because of their high velocity and unusual trajectories. Unlike asteroids or comets bound by the sun's gravity, interstellar visitors appear suddenly, cross the solar system within months or years, and often defy traditional orbital tracking models. The confirmation of such a precise impact trajectory by Webb demonstrates not only the telescope's unmatched capability, but also highlights the fragility of planetary systems when confronted with rogue cosmic wanderers. In the wake of Webb's confirmation, the global astronomical community has mobilized in an unprecedented way. Observatories across the world have redirected their instruments toward Mars and 3I Atlas, capturing every possible detail of the approach. The European Southern Observatory's Very Large Telescope has been measuring subtle spectral shifts in the object's coma, while radio observatories like ALMA and the Square Kilometer Array have been monitoring its emissions for signs of unusual molecular activity. The data collected from these efforts will feed into simulations predicting the exact timing, location, and energy of the collision. The combined resources of multiple space agencies have turned the solar system into a coordinated observational network united by a singular cosmic event. The human fascination with Mars adds a deeper layer of meaning to this event. For decades, Mars has been at the center of our dreams of exploration and colonization. It has been the stage for robotic missions, the target of orbiters and landers, and the imagined destination of future astronauts. Now it faces an encounter that will alter its landscape in a matter of seconds. The area of impact, believed to be somewhere near the equatorial region, may change the planet's appearance as seen from space, creating a new geological feature visible even to amateur telescopes. The aftermath of the collision, though beyond the immediate focus of current study, will transform the planet's surface for millennia. Beyond the physical consequences, the collision carries symbolic weight. For the first time, humanity is observing the interplay between two cosmic travelers, one born of another star system, the other a world that has captivated our imagination for generations. The event bridges scales of time and distance that dwarf human comprehension, linking the fates of two celestial bodies in a brief, spectacular act of cosmic violence. It serves as a reminder of the solar system's openness, that it is not a closed, static environment, but part of a vast galactic ecosystem in which material constantly moves, collides, and evolves. Astronomers are particularly interested in the opportunity to observe the physics of high-velocity impacts under Martian conditions. Mars, with its thin atmosphere and diverse surface composition, provides an ideal laboratory for studying impact cratering and ejecta dispersal. Models predict that the shockwave from 3I Atlas's impact will generate seismic waves detectable across the entire planet. These waves could provide a wealth of data about Mars's internal structure, complementing measurements from existing seismometers deployed by missions like InSight. Such data could refine our understanding of the Martian crust, mantle, and core. and by extension of terrestrial planet formation. The material thrown into orbit could also produce temporary rings around Mars. Simulations indicate that fine dust and rocky fragments might form a diffuse transient halo that could persist for months or years. This would offer an extraordinary chance to study the short-term evolution of impact-generated ring systems, something never before witnessed around a terrestrial planet. The collision might also cause temporary atmospheric effects, including the release of trapped gases from subsurface ice and the creation of a localized impact weather system. These phenomena could reveal new insights into the interaction between impact energy and planetary atmospheres. Meanwhile, the Webb Telescope will play a central role in chronicling every phase of the approach. Its unparalleled infrared sensitivity allows it to pierce the dusty halo forming around 3I Atlas as it nears the Sun. Already, its instruments have detected changes in the object's albedo, suggesting volatile sublimation as sunlight heats its surface. This activity, reminiscent of comets, points to complex organic chemistry and perhaps even the presence of exotic ices rarely found in our solar system. Each data packet transmitted by Webb deepens our understanding of this celestial messenger from another world. Scientists have long theorized about the exchange of material between star systems, a process known as panspermia on interstellar scales. If 3I Atlas carries organic compounds, or even prebiotic molecules, its collision with Mars could represent a natural experiment in cross-stellar contamination. Though speculative, the idea that interstellar objects could seed life across planets and star systems gains new relevance in light of this impending impact. Mars, a planet once thought capable of supporting life, could now be the recipient of material from beyond the Sun's reach, perhaps reigniting ancient biological potential in frozen soil or subsurface aquifers. Another aspect of deep interest concerns the energy distribution upon impact. The kinetic energy released will melt and vaporize rock, forming a transient plasma plume that may rise hundreds of kilometers into space. Webb's spectroscopic instruments will be able to analyze this plume, capturing the signature of both Martian and interstellar elements mixing at high temperature. Such observations could reveal isotopic fingerprints that trace the origins of 3I Atlas and clarify whether it formed in a young, metal-rich system or an ancient one depleted of heavier elements. The results could extend our understanding of galactic evolution itself, connecting local planetary science to the broader story of cosmic formation. The global excitement has not been limited to scientists. The public has been captivated by the unfolding drama, the sight of a world-changing event that, while safely distant, plays out in real time before our instruments. Media outlets stream live data visualizations and artistic interpretations of 3I Atlas's journey toward Mars. Educational institutions are preparing to incorporate the event into curriculums, emphasizing its significance for planetary science, astrophysics, and the philosophy of space exploration. Humanity, united under one sky, is collectively watching as a fragment of another star system meets one of our own planets in a cosmic ballet of motion and destruction. Despite the excitement, the scientific community remains grounded in careful observation. Every element of the event, from the initial atmospheric entry to the formation of the impact plume, will be studied in depth. Even before the collision, the final approach of 3I Atlas is yielding valuable data about the behavior of interstellar material under solar heating. Observations show shifts in the object's rotation rate and spectral changes in its outgassing patterns, suggesting that its internal structure is heterogeneous. Some scientists theorize that it may be a fragment from a disrupted protoplanetary disk, carrying within it minerals and compounds forged in the chaos of another young star. Mars itself stands as a silent participant, its red deserts awaiting the arrival of this alien body. The planet has long borne the scars of impact, from the colossal basins of Hellas and Argyre to the smaller craters that pepper its landscape. But none of those were caused by objects confirmed to have come from beyond the solar system. The new crater carved by 3I Atlas will be unlike any before it, not only in origin but in composition. As instruments scan the aftermath, scientists will seek traces of new minerals and isotopes that may differ from anything found on Mars or Earth. These signatures could help confirm the object's interstellar provenance and shed light on the diversity of matter beyond our cosmic neighborhood. Astronomical organizations have already scheduled around-the-clock monitoring campaigns. The Deep Space Network is preparing to relay vast amounts of data from orbiters and landers, while independent telescopes from Chile to Hawaii will track the optical flash visible even from millions of kilometers away. The Hubble Space Telescope, though surpassed in sensitivity by Webb, will still provide complementary ultraviolet data. Never before has an astronomical event of this scale been anticipated with such a coordinated multi-instrument approach. The collision will serve as a benchmark for how humanity observes, models, and understands dynamic processes across the solar system. The timing of the event adds another layer of intrigue. Mars is currently at a favorable position in its orbit relative to Earth, allowing for optimal communication and visibility. This fortuitous alignment means that both robotic and telescopic observations can proceed with minimal interference. Scientists are planning to use the occasion to test advanced imaging algorithms and data compression methods developed for future interplanetary missions. The data harvested from the impact could also influence the design of upcoming Mars landers, as it will reveal new information about dust dynamics and high-altitude debris behavior in the thin Martian atmosphere. As the date of collision draws near, a sense of awe pervades the scientific world. For decades, the cosmos seemed vast and distant, its most dramatic events occurring beyond reach. Now, an interstellar object, a traveler from another sun, is poised to collide with a world we have explored, mapped, and dreamed of walking upon. The moment encapsulates both the fragility and grandeur of planetary existence. It is a reminder that celestial bodies, no matter how familiar, are still part of a dynamic, evolving universe where chance encounters can reshape the fabric of worlds. From a purely astrophysical perspective, the Webb Telescope's confirmation marks a triumph of precision observation. Its ability to detect faint light across vast distances, to resolve the thermal and spectral fingerprint of a small, fast-moving object, and to refine orbital mechanics to within a fraction of a degree, has turned what could have been a mystery into a predictable and analyzable event. The scientific infrastructure supporting this observation, from data pipelines to simulation frameworks, represents the pinnacle of human ingenuity directed toward understanding the cosmos. The days leading up to the impact of 3I Atlas have transformed into an extraordinary period of anticipation, discovery, and collective focus unlike anything in modern astronomy. The collision's inevitability has pushed scientific inquiry into uncharted territory, and every passing hour deepens the complexity of what is being observed. Webb's continuous monitoring has already yielded a torrent of data. And as the object draws closer to Mars, its every movement, spectral change, and physical reaction is being scrutinized with a fervor usually reserved for historic missions. The once distant and anonymous wanderer from interstellar space has now become the central actor in a cosmic drama unfolding before human eyes. As it nears the Martian system, 3I Atlas has begun to exhibit a remarkable increase in activity. The telescope's readings indicate that sunlight has penetrated its outer crust, warming volatile materials buried beneath. Jets of vaporized ice and gas are now bursting from its surface in irregular intervals, altering its rotation and subtly changing its trajectory. The shifting plumes of vapor form a faint tail, giving the object a temporary cometary appearance. This dynamic behavior is providing scientists with an unparalleled opportunity to study how interstellar bodies react to solar radiation. The patterns of outgassing, far more chaotic than those of typical comets, reveal that the interior of 3I Atlas may contain complex mixtures of compounds never seen before in our solar neighborhood. Each emission, each flicker of reflected light, carries clues about the environment in which it formed. Perhaps in the cold, dim outskirts of a distant star's debris field, or even within the shattered remains of an ancient planetary system. Mars, meanwhile, continues its silent orbit, oblivious to the attention now fixed upon it. Observations from orbiters have begun to record subtle atmospheric fluctuations caused by the gravitational influence of the incoming body. Even though the planet's atmosphere is thin, these disturbances hint at the immense kinetic energy that will soon be released upon impact. Dust suspended in the Martian air has already begun to respond to electrostatic effects from the interaction between solar wind and the charged particles emanating from 3I Atlas's coma. From millions of kilometers away, instruments aboard Webb detect faint, ghostly auroras flickering across Mars's upper atmosphere. Signs that the planet's magnetism, weak though it is being stirred by the onrushing visitor. The approach of 3I Atlas is now precise enough that astronomers can calculate the impact coordinates with near certainty. The collision is expected to occur near the boundary between two distinct geological regions, an ancient volcanic plateau and a vast sedimentary basin. This location is scientifically fortuitous. The differences in mineral composition and crustal density will allow researchers to analyze how shockwaves propagate through contrasting materials. The impact's seismic patterns could reveal fine details about Mars's internal layering, acting as a planetary-scale tomography experiment. It is as if the red planet, through this cosmic accident, is about to disclose its innermost secrets under the probing force of an alien hammer from another star. The human dimension of this moment is equally compelling. Across the world, observatories are operating at full capacity, many for 24 hours a day. Teams of scientists from dozens of countries collaborate through continuous video conferences, sharing live telemetry, modeling data, and spectral analyses. Language barriers fade in the face of shared curiosity. The boundaries between space agencies dissolve as NASA, ESA, Roscosmos, CNSA, JAXA, and private research institutions combine their instruments and expertise. It is a rare moment of global unity in the pursuit of knowledge, a recognition that what happens between 3I Atlas and Mars belongs to all of humanity. The implications stretch beyond science and into the realm of philosophy. For centuries, humankind has looked at the night sky with a sense of separation. Distant stars, unreachable worlds. Now the reality of an interstellar object colliding with a familiar planet forces a reevaluation of that distance. It is a tangible demonstration of cosmic connectivity, a physical bridge between solar systems. Every atom of 3I Atlas carries a lineage that began under a different sun, possibly in a region of the galaxy hundreds or even thousands of light years away. Its journey across that void and into the gravitational influence of our solar system blurs the notion of cosmic isolation. The universe, long thought to be vast and fragmented, reveals itself as an intricate web of motion and exchange. In laboratories on Earth, chemists and planetary geologists are preparing for what they might detect after the impact. Even though no direct samples will be available until future Mars missions, the plume of material ejected into space will be observable in exquisite detail. Spectrometers aboard orbiters will capture data on molecular composition and isotopic ratios within seconds of the event. Every element identified will tell a story about conditions beyond our solar nursery. If compounds are discovered that contain isotopic distributions impossible to form in our system, it would confirm that 3I Atlas carries fingerprints of another sun's nuclear history. Such evidence would be a revelation, linking stellar processes across the galaxy through a single spectacular collision. The immense energy released by the impact will transform the immediate environment around the site. As 3I Atlas plunges into the Martian surface, the shockwave will propagate outward at supersonic speeds, melting rock and vaporizing layers of regolith. The airburst, though occurring in a thin atmosphere, will still produce immense heat and pressure, briefly turning part of the sky into a glowing plasma. Observers expect to witness a transient bloom of ultraviolet and infrared radiation visible even to Earth-based telescopes. For a few minutes, Mars will outshine all other objects in its region of space, becoming the brightest point of light beyond the moon. Webb, along with other observatories, will record these emissions frame by frame, capturing the birth of a crater and the dispersal of energy in a way never before possible. The aftermath of the initial strike will unleash secondary phenomena. Some of the ejected material will escape Mars's gravity entirely, forming temporary dust streams that will intersect with the planet's moons. Phobos and Deimos will likely experience micro-impacts as fragments of both Martian rock and interstellar debris rain down upon them. The interaction could alter their surface properties, darkening their regolith, or even introducing trace elements of 3I Atlas's exotic composition. The event may indirectly seed these small moons with interstellar minerals, creating a unique archive of mixed material waiting for future missions to study. Among planetary scientists, there is growing excitement about how the collision might reshape the Martian surface in ways that could later aid exploration. The immense heat and mechanical force will expose subsurface layers that have been buried for millions of years. These layers could contain ancient ice deposits, salts, or fossilized sediments from Mars' wetter epochs. In essence, the impact may act as a massive geological excavation, peeling back strata that robotic drills could not reach. Future rovers may one day explore the rim of the new crater, examining freshly revealed materials that hold records of both Martian and interstellar history. In the scientific narrative of planetary evolution, such a collision represents an accelerated experiment. Researchers have theorized for decades that impacts play a crucial role in shaping planetary surfaces, altering atmospheres, and even influencing potential habitability. Now they have the chance to watch one unfold in real time. The thermal evolution of the impact site, the cooling of molten rock, the condensation of vapor, and the reformation of solid crust will be tracked over months and years. Webb's infrared instruments will monitor residual heat signatures, while orbiters will map changes in albedo and mineralogy. The data will help refine models of planetary recovery and provide insights into how Earth itself might have responded to similar events during its early history. One of the more fascinating hypotheses emerging from the event concerns the possibility of creating new minerals under extreme conditions. The pressures and temperatures generated by such a high-velocity impact could synthesize compounds that do not naturally occur on either body. Scientists anticipate that within the impact melt, transient materials might form ultra-dense crystalline structures or novel glassy phases that preserve traces of both Martian and interstellar chemistry. These would serve as physical markers of the collision, tiny monuments to the meeting of two worlds. When future explorers retrieve samples from the site, they may hold in their hands the literal fusion of two cosmic origins. In addition to geological insights, the event will also provide valuable data for understanding the physics of interstellar bodies. The fragmentation pattern of 3I Atlas as it enters the Martian atmosphere will reveal details about its internal strength and porosity. Whether it shatters into fine dust or remains largely intact before impact will indicate whether it is composed of loosely bound rubble, compact stone, or icy metal. The distribution of fragments, their size range, and their dispersal across the surface will help refine models of how interstellar objects are built and how they survive their journeys across interstellar space. These findings could prove essential for identifying and classifying similar bodies in the future. Even now, 3I Atlas remains a source of surprises. The latest data suggests that its rotation has begun to accelerate, possibly due to asymmetric outgassing. Its shape, previously thought to be elongated, appears to be more irregular than anticipated, with concave surfaces that catch sunlight unevenly. These features contribute to unpredictable variations in brightness, making photometric analysis challenging but deeply informative. Each irregularity in its light curve is a clue to its structure, perhaps hinting at cavities, fissures, or complex layering within its interior. Such irregularities could be remnants of its birth in a chaotic stellar nursery where gravitational forces tore at forming bodies. Meanwhile, Mars's orbiters are capturing the slow crescendo of visual tension as the object grows brighter against the black backdrop of space. From the Martian surface, were one able to stand beneath its dusty sky, the object would now appear as a fast-moving point of light, its brightness increasing nightly. Its arrival is not silent. Though sound cannot travel through the vacuum, the vibrations it will unleash within Mars will ring through the crust like a planetary bell. Seismometers already on the surface are calibrated to record frequencies beyond their original design specifications. These vibrations will provide a direct acoustic image of the planet's interior, offering information about density transitions and hidden mantle structures. The impending collision, catastrophic though it is, will expand humanity's understanding of planetary anatomy as nothing else could. The philosophical and cultural resonance of this event cannot be overstated. The collision represents more than a scientific occurrence. It is a reminder of cosmic impermanence. It underscores the reality that planets are not eternal bastions of stability but dynamic participants in an ever-changing celestial dance. For civilizations that look to the stars with dreams of colonization, it serves as both inspiration and caution. Even in the grand theater of the universe, worlds can be reshaped in an instant by forces beyond comprehension. Yet within that destruction lies creation, the birth of new forms, the forging of new elements, and the continuation of cosmic evolution. In classrooms and observatories alike, students and enthusiasts are captivated by the unfolding story. Artists have begun to interpret the collision through sculpture, digital imagery, and film, attempting to capture the grandeur of a meeting that transcends human history. Writers and philosophers debate its symbolic meaning, whether it reflects the inevitability of change, the merging of worlds, or the delicate balance of cosmic order. The impact of 3I Atlas with Mars has become a touchstone for the imagination, a living event that combines science with the emotional magnitude of witnessing something fundamentally transformative. Technologically, the preparations for observing the impact have pushed the limits of human capability. Ground-based telescopes equipped with adaptive optics are now achieving resolutions once thought impossible, rivaling orbital instruments. Supercomputers simulate the expected outcome of the collision using complex fluid dynamics, modeling the interplay of heat, gas, and dust as the object disintegrates. These simulations help scientists anticipate what Webb and other instruments will see, ensuring that no moment of the event escapes documentation. The coordination effort represents one of the most complex data operations in the history of space science, involving petabytes of information transmitted and analyzed across continents in real time. If you like this video, please give it a like and subscribe to our channel. Also, could you leave your comments below and tell us? What are your thoughts on 3I Atlas heading toward Mars collision? We want to hear from you. Thank you for watching, and see you next time.